So welcome everybody once again. So we are in the third class, but it's the second topic that we are looking at. And this is a kind of a summary of what we have done already in terms of the feedback from you, especially from the civil engineering people and a few other backgrounds. We saw what could be the main distinguishing factors that we will see in flight vehicle structures as opposed to many of the other areas. In particular, we will look at civil engineering structures because there's a drastic difference over there. So let's take, oops, oh, it doesn't. Huh? Oh, I see. Oh, I see. Okay. So it's either this or that. Okay. Okay, so this is what we will, to start with, look at. How are the flight vehicle structures different from static or civil structures like the main building that you have at the ISC campus? This is basically a aircraft which flies on solar power, one of the demos that you might have seen in the news as well. Irrespective of what type of aircraft we are looking at and what type of civil engineering structure we are looking at, or for that matter, any static structure that you have could be stationary machinery, for example. The primary thing is that this is a moving structure and it's moving pretty fast compared to especially land-based vehicles, unless you have an exceptional case like racing cars, etc. Most situations it is moving so fast that the efficiency of the motion becomes very critical. How much of fuel burn you have for a particular passenger kilometer that you would like to have, if it's a passenger aircraft, or a cargo, if it's per kg, per kilometer, how much of typical, like how you deal with mileage on your two-wheelers or four-wheelers, very similar to that. The fuel burn becomes a very big concern, and one of the main ways of reducing it is by reducing the weight. There are many other ways of doing it. Of course, the propulsion people will be looking at enhancing the efficiency of the engines that are being used. The fuel chemistry people will be looking at better and better refined versions of the fuels to improvise that. The aerodynamics people will be trying to reduce the drag. So everybody has a contribution towards it, but one of the major contributions is towards weight. In terms of a small reduction in weight can have usually a very huge increase in performance. For example, it could be traveling a larger range. In other words, the aircraft's capabilities to serve more airports might become possible. It could have more number of passengers and or their baggage, and therefore it becomes a better saleable option for the airlines that are going to operate them. It could travel faster. Once again, competitive advantage for one airline over another. If it's operating a faster aircraft on an average, people might prefer that, with even if it's a saving of 5-10 minutes over a short haul. It can, on a long haul kind of an aircraft, become a saving of an hour or so. So all of that becomes very critical, that we reduce the weight as much as possible, but at the same time, obviously, it has to be strong and stiff enough. Strong because you don't want the materials to fail, and stiff because you don't want the aircraft to deform too much, because once it does, for example, if an aerodynamic surface deforms too much, its airfoil cross section may not be what the aerodynamicist designed it for, and therefore you would have a lower L by D or lower performance CL max, let us say, or any other thing. The stall angle could change, various other parameters could change, which in turn would affect the overall performance of the aircraft. So there are particular structural components for which the stiffness is more important than the strength, and for some where the design is more strength driven rather than the stiffness driven. For example, if you are looking at, let's say, deploying an antenna out of a spacecraft, the orientation of that antenna, if it's especially a long antenna, let's say, becomes very critical, and therefore the deformation becomes the critical thing, and the design would be more stiffness driven. It's not that strength will not be given a consideration, but between the two, in terms of the priorities, you would be looking at one over the other, and only then later you'll be looking at the other. So these two concepts we already looked at earlier, the specific strength and the specific stiffness, which is just dividing by the mass density of the material that is used, so that we have per unit weight of a particular component of a given volume, which will offer the greater strength or stiffness for a particular application. Usually the problem is comes in a different direction, where you're looking at, you already know a particular design ultimate load for the particular application that you have, and then there is a design limit load. So design limit load is driven by the VN diagram, or the flight envelope of the aircraft, where you find out the most critical operation limits of the aircraft, and based on that you can arrive at some kind of a design limit load, which is the maximum lift to weight ratio that the aircraft might experience, both in the positive and negative sense, and therefore what kind of loads that translates into for the structural components. Then this particular ratio of the design ultimate load to the design limit load becomes what is your factor of safety, typically taken as 1.5. So based on that, the choice of material and also the choice of the shape and the size of the structural components is typically carried out. So if I got some feedback from some of the students that they don't understand some of this terminology, just don't bother about it. The whole idea of me repeating some of this terminology is for you to get used to those words, but we will be looking at each one of them in terms of a more precise definition as we go forward. So it's okay if you don't understand, but if that's something which is bothering you, please stop me, and we can spend a minute or two trying to discuss some of those particular terms that you might be totally unfamiliar with. So once we know that specific strength and specific stiffness are the governing features, we know in terms of the material choice, that is what is important. But this, as I already told you, there are two ways in which a structure can be a better structure in a sense of better load bearing capabilities. One is through the choice of material, the other is through the choice of the geometry. And geometry again is two parts to it: the shape of the structure and also the sizing of the structure and the structural components. As far as the overall size and shape of the structure is concerned, usually the structural engineers do not have much of a say over it, because in terms of the overall size, it's typically driven by the mission that this aircraft has to accomplish eventually, the primary missions that it has to accomplish. So there is an RFP based on that. What is the requirements that you would have based on the mission requirements, and therefore how it translates to the design. So the overall sizing of the aircraft is done, for which typically people look at comparable aircraft of the similar size and or similar missions rather, and then arrive at the kind of potential ballpark range of weights and or whatever you might have. But since that old design, the materials technologies would have improved, the production technologies would have improved, the various manufacturing new paradigms that are coming in, for example 3D printing or additive manufacturing. So how some of those can be utilized probably in certain aspects, and how that can help moving forward. In the initial stages, there might not be too many early adapters, especially for these large-scale deployments. For example, additive manufacturing, when it started off, it was mostly for plastics, and later on it came for metals. When it came for metals, it was using as a raw material the powdered metal form as the raw material, and therefore the strengths and stiffnesses that you could get out of additive manufacturing were not of that good quality as with the conventional subtractive kind of manufacturing. But over time, instead of let's say powder form of raw materials, you went into wires. For example, it's very commonly used in titanium, which is many titanium parts in aircraft today for almost 10 years now have been manufactured, especially replacement parts, etc., using additive manufacturing. And some of these use wires, titanium wires, as the raw materials. In other words, the additive manufacturing technology has also grown, and with that, the properties that are desired apart from specific strength and specific stiffness, there are many other required properties, like for example, the corrosion resistance that it could have, the fatigue resistance in terms of what is known as an SN curve, strength versus the number of cycles of loading, how the strength reduces with the number of cycles of loading. These are characteristics of the material, and these material characteristics can improve not only with the choice of the raw materials, but also the production process that is involved, and all of these are continually evolving and need to be taken advantage of. So that's as far as the material is concerned. As far as the geometry is concerned, as I already mentioned, the overall geometry is dictated by the mission, and once the overall geometry is decided, the overall aerodynamic design is what will give you the overall shape, especially of the lifting surfaces, the wing and the horizontal tail, the vertical tail, all of which are going to be contributing towards the actual stability, control and performance of the aircraft. All of that will typically be dictated by non-structural decision-making process, of which the structural engineer is usually a part, that some of the members of the structural engineering team usually participate in those discussions, but the requirements are driven by the aerodynamicist and the theories associated with that, the modeling associated with that. So that's as far as the external shape of an aircraft is concerned. But once the external shape of the aircraft is decided, as far as the internal shapes are concerned, that's where the structural engineer comes into the picture as well. So this is a Boeing 787 aircraft model that you see over here. And so it's the overall shaping of the fuselage, the overall shaping of the wings, the horizontal tail, the vertical tail is missing thanks to my daughter. Anyway, so the overall shaping is done by the aerodynamicist. But once you take a particular component, let's say one of the wings, how internally it is made, how it is structured, what is the thickness of the shells that are going to be used for the top surface here, what the bottom surface over here, and what are the reinforcements that are going to be used, what cross sections they might have, what materials go into them. And in that, the internal shape, it could be an I section, it could be, for example, the stringers could be a T section or a channel section, which is better for which particular application. All these entire decisions have to be made by the structural engineer, but they have a certain budget within which they have to do it. Budget not only a monetary sense, but weight budget as well. So the overall weight of the aircraft is what dictates the performance of the aircraft as a whole in terms of its range, endurance, the maximum speeds it can achieve, the maximum altitudes that it can go to, number of passengers it can carry. All these things are dictated by these particular things. So once that is done, the overall shaping is done, the internal fractions that you have, some part is allocated to the payload, some part to the fuel, depending upon whether it's a long haul or short haul, the amount of fuel fraction could be quite different from each other. Then once that is decided, whatever remains for the avionics that has to be taken out, then you have, of course, there are many other miscellaneous things, but I'm talking of only of the major components over here, the engines, etc. And then what you have remaining weight portion, that is the range in which the structural engineer has to operate. And if the structural engineer can come up with a design based on newer materials and or newer shaping and sizing options, and also the distributions. It's not just the shaping and sizing of components, but where you place them. So you could have, let's say, 3 or 4, let's say, spars for a large aircraft, and those 3 or 4 spars, where along the chord would you want to place them? So based on that, the cross section of the spar that you would want to have could be quite different. Some cases it might require a larger cross section, which means a larger weight penalty, etc. And so you have to optimize, one is the material, optimize the shape, optimize the size, and optimize the location, that in terms of how they're going to be distributed. Also, you might have to make a choice of whether to have 2 large cross-section spars or maybe have 3 medium cross-section size spars. So all of these decisions will have to be arrived at by using the appropriate theories which are reliable enough, and eventually, of course, it has to be experimentally tested both on specimen levels as well as eventually component levels, and finally the prototype testing as well. And there are lots of certification based testing that one has to be looking at. So the next thing is the geometry. Of course, is in the case of the aerospace vehicles, typically turns out to be more complex compared to many civil engineering structure. But of course, here, because of the kind of strong materials like cement and the steel reinforcements that we have had, the RCC in particular, people have gone into kind of fairly arbitrary shapes, because of which, if you look at the weight percentage of how a building is utilized typically, if you look at in the same sense of what we do with the aircraft, the payload fraction, how much of people are there, how much of their furniture is there, all of that as a fraction of the overall weight of the building, this is a very, very inefficient kind of a design compared to what you have. And in the initial stages, as humanity developed, the human civilization developed, there was a lot of utilization of natural materials, and their composites were again playing a huge part. If you look at materials like which have been used for thousands of years, both in India as well as West Asia and a few ancient European civilizations, and also the South American, North American civilizations, you would see that cob, for example, is a very common material where you use clay, sand, in certain proportions, and then you also have let's say straw, which is typically added, not hay. Hay typically will rot, but straw is essentially a plant-based dried up grass kind of a thing. So you have that. So you see that it's essentially a composite. So you have a reinforcement that you have over there. So conceptually, humankind has been looking at it, and in fact, not just humans. If you look at the way birds build their nest, to have it strong enough to hold their eggs, you would see that they use a lot of straw, they use a little bit of mud, and all of these combinations are typically there. So we have kind of evolved from this whole thought process from biology, from what we observe in nature, and taken it forward. But once we came to engineered composites like RCC, what happened is we could build shapes which were much more complicated, more than from functional point of view, it was more from an aesthetic point of view. So what the aerodynamicist, what kind of penalty he gives for the structural engineer and flight vehicle structures, typically the architect does that as far as this is concerned. So you typically have that. If you look at it in the medical field also, if you look at the human body, the structure is the structural loads, the load bearing element is essentially your skeleton, the bone, which is a composite. But what covers that is essentially what you're looking at from an aesthetics point of view. Of course, there are many layers to it, but eventually at the end of it is the dermatology or the skin that you're looking at. So you can look at the aerodynamics, the kind of things that they're giving is essentially from that point of view, from the outer function point of view. From the inner function point of view, how you design the, how nature designs the skeleton, how a bird designs its nest, all these things are essentially coming into a paradigm very similar to how the structural engineer is essentially designing these things. So apart from cob, people moved on to what are known as adobe, which is basically your bricks, which are either baked or raw bricks, which are just sun-dried kind of bricks. Then you have what is known as super adobe, where you essentially fill this mud into bags and you then ram them. There's also another concept of without putting into the bags, you have rammed earth. So you have rammed earth kind of buildings. So essentially what you're doing is you're compacting this material, and as we go forward with the flight vehicle structures which use composites, we will see that there are a lot of these concepts from not actual the process itself, but in terms of the conceptual nature, it's very similar to what we have been doing with many of these building structures. So in other words, a lot of the learning that we get from other branches of engineering usually help us in aerospace engineering. Whereas a lot of new materials that we are developing because of our much more stringent requirements, some of those materials get spun off into various other applications, including biomedical, etc. You would have seen various options where, for example, artificial limbs, etc., being made much lighter by using modern composites compared to what they were using earlier in terms of, yeah. You had some question? Okay, fine. So, so you have those differences that are there in different fields, but we can all learn from each other and how we incorporate those things, not by blind copying, but an appropriate adaptation to the requirements that we have in our field is what is the way to go forward. So one is in terms of the complexity of the geometry because of the aerodynamic requirements. The other is in terms of the lower tolerance levels that you would have because of how narrowly you're operating in terms of the factors of safety. Therefore, the tolerances that you have in terms of the geometry, how thick a particular structure can be. So when you're designing this beam, for example, as a civil engineer might say it's about 1.5 feet. If it's half an inch more or less than that, they wouldn't bother too much unless there's some fitting issue somewhere. Most of the time, the tolerance levels in terms of percentage, if you look at, are usually much larger in civil engineering structures, whereas in the case of the aircraft, the thickness of, let's say, a fuselage skin, even a small, let's say 1% change that you have can make a huge difference because it's spread over such a large area that the weight penalty might become too much and or many other repercussions would be there, which will have to be avoided. So therefore, the tolerances that are required are much lower. Okay, I don't know how to go back on this. Anyway, dynamic loading is the other thing that many of you pointed out, especially some of you civil engineers. I think only one was there, right? Yeah. So you pointed that out. So in terms of the dynamic load and dynamic load, yes, you would have seismic loading. You could have a hanging bridge which is having its vibrations, etc. But the kind of dynamic loading that we require to consider in aerospace engineering is over a much larger bandwidth. So in other words, the range of frequencies over which these have to be considered is quite large. In other words, you could have various modes of vibration. This could, one of the dominant modes is the flexural mode because of the lift distribution, the wing tip going up and down. Typically in very large aircraft, you could see as large as 3 meters deflection of the wing tip up and down, and in certain maneuvers, you could even, of course, depends on the aspect ratio, it could go as large as 7 meters. So it's, in other words, it's a visible deflection that you're talking about in terms of the tip deflections that you have. If you look at that is one level of one kind of mode. Then because of the drag, there is another kind of vibration that's happening in this way. So it's another flexural mode, but bending in a different direction. Again, the way the aerodynamic pressure and the shear is distributed around the wing, you would see that it can cause a torque. And that torque again is causing a torsional deformation. That's also dynamic in nature. So you have a torsional modes that you could have. And then in this case, it may not be much in terms of the axial load, but in the helicopter rotor blade or let's say wind turbine blade, etc., you would have the axial centrifugal loads being some of the primary determinants in terms of the design parameters. So you would see that the axial vibration also becomes very critical. And because of the way this geometry is constructed, even if you didn't use composites, all of these can get coupled. In other words, because of the wing sweep that you have, the way the tapering is done, because the chord is much more over here, the chord is much lesser. As you go to the wing tip, you even have a winglet, and therefore the geometry itself changes discretely rather than continuously as you go. Then you have also you have these concentrated loads apart from the distributed loads because of the weight of the engine, also because of the thrust of the engine. So these are going to cause, and also if you look at, usually the fuel tanks are housed in the wing, so which means that as you carry out your flight towards the end, you're using up a lot of this fuel, and therefore the weight distribution changes, and therefore the earlier that weight was actually compensating to some small extent the lift distribution. In other words, it was giving you some kind of a relief But now as the fuel gets depleted, you see that that weight comes down. Still the structural weight is there, the weight of the engines is there, etc. That is offering you some relief, but some percentage of the relief has come down. So how it changes as the flight progresses is also very important. The same considerations in terms of the stress analysis, strain analysis data that you have for let's say close to starting the cruise and close to stopping the cruise and descending, these two might be quite different from each other because of the fuel burn that you have had, and therefore the weight distributions differences that have taken place. Usually it is in a symmetric fashion, so you do not have moments like that, but nonetheless the moment that comes from a particular wing onto the fuselage undergoes a change. It could be larger because the fuel has depleted, and therefore the lift you are still having the same because you are still cruising towards the end phases of your cruise, and therefore of course you want to, in the cruise you want to match the lift to the weight, and therefore the overall weight has reduced because of the fuel weight has reduced. But nonetheless what we are talking about is just a particular structural component, how it is changing its distributions, and some of these can get affected. So again also depend that in turn dictates how you will design within the wing the fuel distribution, the shape of the fuel tanks, how they are going to be, etc., etc. Another important point is as we move to composites, especially when we go to carbon composites, the carbon is not an issue because it's a conducting material, just like aluminum alloys which have been used for a long time for making aircraft, and therefore lightning strikes, for example, was not a problem. But in the carbon fiber cannot take the load by itself. It can only take tension, but bending involves compression as well, and therefore you need to put it into a matrix. So there are many other reasons why you need a matrix, which is essentially a resin into which you put the fibers, but then the resin typically is epoxy or any other resin that is typically used as a plastic and is an insulating material, and therefore a lightning strike you have to be very, very careful with, because it's all about the galvanic corrosions that can result, and also whether the voltage that is coming out of the lightning strike, whether it reaches the fuel tank. Some of the initial stages of human flight, there were quite a few accidents where the fuel tanks caught fire because of this. So a lot of chemistry goes into this decision making in terms of the galvanic table you look at, how far these materials are from each other. And in particular, I'll show you the Airbus A350 as well later, but that's about 4 years after we started off with the Boeing 787. In terms of the design, there were huge design delays in both the cases because of the new materials that are used and various other new technologies which have been used. Both of these are about a decade or decade and a half old technologies, but we haven't had any major passenger aircraft program since then. So this is the probably the latest we have in terms of technology in that category of aircraft. So that's the reason why I'm referring to them. But so as I said, the chemistry plays a very critical role. So if you're using carbon fiber composites to reduce the weight, which is very good because you're increasing the overall efficiency of the aircraft and therefore the performance, but then you might run into other kinds of problems. There are certain regions and certain locations where you cannot still use composites. So even in these best case scenarios of the, can you just open this for me? In the best case scenarios of the Airbus A350 and the Boeing 787 Dreamliner, you have about 50 to 52% by weight, structural weight. You see will bring down the structural weight by about almost 35% overall. But if you're looking at the overall structure, what all it is made out of, it is essentially what you're looking at is, so you see this is Airbus A350 extra wide body. So this is the XWB version. In each of these, the Boeing 787 as well as the Airbus A350, there are many, many variants to it. Not too much of a difference in terms of the overall structural design, but various other parameters in terms of the capacities, the ranges, and a few other things that they are differing by. But essentially what I'm talking about is in both these cases, composites in general and carbon fiber composites in particular were used extensively. But once they are used, even though carbon being electrically active, with the fact that you have the epoxy as an insulator was causing some issues, because of which you wanted to have elements which are as close to each other as possible in the galvanic table. So in the galvanic table, if you look at the element that we used to use extensively in aerospace earlier was the aluminum, of course as alloys, but the primary element of those alloys was aluminum. And that aluminum, if you combine with carbon fiber, they are very, very far away in the galvanic table. You can check. You would have studied in your high school and high school physics, etc., chemistry. So you would see that the electrochemistry there is very, very strong between aluminum and carbon, even when you have the epoxy in between them. So what people observed is that you can't do away with the metal completely. There are certain regions where you need the metal because composites have their own disadvantages as well. One, for example, is the impact resistance. So impact wise, metals seem to be performing better because they're ductile in nature, so you can know a damage that has occurred and then you can rectify for it. A lot of the damage in the composites might happen internally and it's brittle in nature because of the epoxy matrix that you have, and it could fail suddenly, and therefore you could have issues. So impact, so certain regions which are prone to impact, for example, bird hits are quite common. Again, the engines are missing thanks to my daughter. So you look at the engines on this. So typically on the engines there could be bird hits. So again, on the leading edge of the wings as well as the horizontal tail and the vertical tail, you could have the bird hits that are possible. So now that's an impact. Even though a bird you might think of as a soft material, a soft tissue, and not very heavy. Most flying birds at least are not very heavy, but the kind of speed at which the aircraft is traveling and then the bird hits it, that could have quite a large amount of energy of the impact, and that has to be absorbed by these materials. So typically you may not have composites at the leading edges of the wings and the tail, and also certain parts of the engine which are exposed to that. There are of course many other reasons why, especially in the latter parts of the engine, you would not use a polymer based composite because of the temperatures are much higher, and that is not possible over there. Yes.
So you mentioned something about the galvanic.
Yeah. Sure, sure. So you would have seen typically in terms of the EMFs that you have and various materials that you have, you would see that typically this could be going from negative values to positive values. So you are having, let's say, I'm not exactly sure of the numbers, but I'll just give you a qualitative sense of that. So this would be typically your aluminum over here. You would have, let's say, carbon over here. So in other words, the potential difference that you're going to have because of this is fairly large. If you have some other material which is, let's say, over here, then the difference is much lesser, so the chances of the galvanic corrosion happening are much, much lesser. So what you're essentially talking about is that, for example, in metals, for example, if it's a steel or iron, you could see the rust, and it's kind of visible, and over time people can make certain changes to it, or they can have coatings for it to avoid it in the first place, or delay it to whatever extent. But in composites, this becomes a little more dicey. So instead of using aluminum alloys, one example of what is over here is titanium. So titanium alloys, for example, are much closer to carbon compared to aluminum alloys in terms of their EMF, and therefore you have the galvanic corrosion issues much lesser when you use these two as a combination. But there is problems. This the cost of this is going to be much higher that you have because of its availability. Aluminum is much more widely available, so its cost is typically much, relatively speaking, at least for the alloys that we are considering, it's much lesser compared to the titanium alloys. So you would see very strangely, though titanium, another reason why people do is its uses its high temperature capability. So compared to the aluminum alloys, typically you would have the high temperature capabilities are much more. So for example, we're talking about the engine, there are certain portions where aluminum alloys may not be usable because of the higher temperatures, but you might be able to use titanium alloys. So people were surprised when, to start with, you had in these aircraft, both of these, almost you would have, I think, about 15-16% of titanium alloys. People were surprised. Titanium alloys used to be used mostly in fighter aircraft, supersonic or close to hypersonic kind of ranges, where you had issues of higher temperatures, and therefore you needed higher temperature capability materials, and they were produced in certain smaller quantities, and also they were not being regularly utilized in an economic sense. It's more of for the armed forces, etc., and therefore you're willing to spend a little more, and which is where you saw that most of the titanium alloys were used. But for the first time in passenger aircraft, you saw large usage of titanium. People were okay with composites. They knew the specific strength and specific stiffness are very high for composites, especially carbon fiber composites, and therefore their being utilized made a lot of sense. But once you saw that, titanium was used, people it raised their eyebrows.
Can you tell us, I mean, the places in an aircraft where we are allowing a large deflection, especially in the wing areas, what kind of material we use? Composites or alloys?
Yeah, a good question there. See, when you want to allow for large deformations, you want to use a lower stiffness material, right? Yeah. So when you want to use a lower stiffness material, you would like to see if you can tailor that stiffness, because you do not want deformations happening in all kind of random directions in random ways. You would want to tailor that deformations. Just like a tailor stitches a particular cloth to your body size, it may not have a good fit for somebody else. Same way in the case of an aircraft, when it is taxiing, when it is climbing, after takeoff, then when it is cruising, performing certain maneuvers, descending and taxiing again, and after landing. So each one of these have certain requirements in terms of what is the optimal airfoil cross section, for example. So good that you asked this question at this point of time, because these looked at, especially the Boeing 787, looked at supercritical airfoils. So these supercritical airfoils, even though these are not, remember, supersonic aircraft, these are transonic, typically operating at around Mach number 0.8 or around that. But nonetheless, the way the air flows around it, there are certain regions where it can locally go into supersonic levels, and therefore the wave drag can become an issue even in transonic flight. And so in such regions, you would want to see that you have a supercritical airfoil, which is something that is used for supersonic aircraft usually. But then you would want its shape to change in a certain way. So essentially what you're doing is morphing. So you're trying to morph it in such a way that you have near optimal, if not optimal, shapes for each of these flight regimes, because the kind of airfoil cross section you would want to have for each one of these is quite different to reduce the fuel burn for a given accomplishment. So you would want to slightly change that shape. So the way most people are trying to do that, at least for future aircraft, is by using what are known as smart materials. So smart materials where the material can actually sense and actuate itself. So it's a self-sensing actuator essentially, which is also load-bearing. Again, the inspirations are very similar from our skin, the way our bodies adapt when we go to a hotter climate or a colder climate, or when you have a jet lag, etc. There are many different ways in which it adapts itself. For example, when there is a cut, you know that typically the blood clots, and therefore it seals itself. So it's a kind of a self-healing kind of a material. So some kind of way in which you are adapting to the environment. So living beings have always been doing that. Otherwise, you as a species, you are no longer there. So you become extinct, right? So what actually happens here also is that it's not so much of a difference, but here even a small saving that you can have in the fuel burn over a number of flights means a huge benefit for the economy of the airline, and therefore the passengers and the whole ecosystem as a whole. So one of the more promising ways of doing it is something by using these smart materials. Another way in which it has already been used right from the beginning of flight is in terms of your control surface deflections. Because once your control surface deflects, a flap of or an aileron, or you have the elevator or the rudder, once it deflects, you know that the airfoil cross section has overall has changed. And by that, the L by D ratios, the CL alpha, the CL max, all of these can have a change depending upon exactly how that deployment takes place. There are also leading edge devices like leading edge slats, etc., which are utilized. So once you have all of these deployments, you are essentially changing it, but that's in a macro sense. It's not at the material level, you are doing it at the structural level overall in terms of having certain controls which are being operated by the pilot, or it could be the autopilot which is doing it in an automatic sense. But what we are trying to do is to see if we can build that intelligence into the material itself so that it can modify itself in a certain way. So that is a much more efficient way of doing things. So whatever you do, if you're doing it at a larger scale, it involves more energy and it is more inefficient. When you're trying to do it at a lower length scales, it is usually much more efficient. So when you're doing it at the material level, it's happening at the microstructure of the material, and therefore most of these kind of operations of changing the shape, for example, changing the size, for example, are not going to be so energy consuming. So that's the reason why you're typically going towards that. Does that answer your question, or you have a follow-up?
Actually, I'm asking that in general, carbon composites, if we talk about, they are brittle in nature.
Correct.
So if we try to, if we permit a large deflection, there is a chance that they will go beyond their. There is a chance that they will go beyond the elastic limit, and if they reach the elastic limit, there is a sudden fall. But in case of metal or metal alloys, we have a fairly large plastic regions.
Yeah.
So there is a possibility that at least we can avoid failures. At least so.
Right.
I mean that will be beneficial in the point of deflection.
Yeah.
But at the same time, we are also compromising the specific weight also.
Right, right. Very good question. See, there are multiple parameters that you have to work upon. One is what you brought up is in terms of the ductility of the material, whether it's brittle or ductile, and how ductile it is essentially the difference between your yield and your ultimate failure. But even if you look at yield itself, the composites, many of them, especially the carbon composites, which are typically used at the typical volume fractions that you have a much larger failure strength compared to even the yield strength, leave alone the ultimate tensile strength of many of the materials that have been used. So in that sense, you're still operating within that safe range, and because you're using a brittle material, you're aware of that fact, and therefore you don't have that leeway of getting into that inelastic regime and then still surviving. So you have to design, because you know that you're designing with that particular material, you have to ensure that your design loads are well within the maximum that is capable of, and that is usually not a problem. But also in terms of the testing, the kind of the frequency at which you make certain inspections, and not only visual inspections but also non-destructive testing that you have to do. All of these will be quite different for composite materials as compared to the aluminum or any other alloy that has been typically used. So this is how this is typically done. Again, it's not just the material differences, also the manufacturing process matters. Sometime back we were talking of additive manufacturing. It could be the same titanium component which is used in an aircraft. One is designed, let's say, or manufactured using conventional technology. Other is using the additive manufacturing. Then you would see that the requirements in terms of the maintenance, etc., is quite different. This in terms of certification also. In fact, the first titanium additive manufactured part which was certified was for the Boeing 787 Dreamliner. So you would see that the requirements have to be tailored from the material point of view, as well as various features of it. So the point that you brought out is very, very important. How the failure happens, whether it's a brittle fracture or is it ductile, that dictates. But at what level? If the brittle fracture of the composite at such a high stress value compared to what is the yield of the metal, then it really doesn't matter. But in terms of the deflections, what you're looking at, especially when you're looking at stiffness-based design where deformation is not required, you would want to avoid deformations or reduce or minimize deformations, then again these large stiffnesses become very, very critical. And again, within the same material, there are various ways. For in steel itself, you know, there's high strength steel as well as larger stiffness steels. You have the carbon content that can be tailored. Similarly, in the alloying. So similarly, in the case of the carbon fiber composite also, the carbon fiber, how it is made. Is it from PAN or various other base structures, base materials from which it is prepared? Depending on that, either you could have very large strength fibers or you could have very large stiffness fibers, may not be both simultaneously. So you have to choose the carbon fiber that you want to use in your carbon fiber composite based on the particular structural component. What is more important to it? Is deformation more important to it to reduce it, or is the failure because it is very close to it can experience in the actual flight, it can experience very close to the its failure limits. So therefore, should I move the strength further away? So based on that, you would choose the particular carbon fiber. So all of these are taken into account. So yes, it is a disadvantage in that sense. Brittle failure compared to ductile failure is a disadvantage because you don't know and it suddenly happens. But it suddenly happens at such a large value that may not even be of concern for most practical purposes. Right? Anybody else? Any questions? Yeah.
Still, composite fibers we are not subjecting in a aircraft where the high loads or impact loads are coming.
Correct.
I believe it's using for fairing purpose.
Correct.
Where it will be only used to be cover some area having a little bit.
Yeah. Yeah, yeah. See, impact is only one type of load where composites don't do very well. But for example, if you look at fatigue, for example, many the structural components are subjected to fatigue. There, composites are much better than metals. Okay, so you would see that depending upon the particular component, what kind of dynamic loads it is being subjected to. Is it like, for example, I was pointing out regions which are more prone to impact, which could be the leading edge, could be certain engine front portions, it could be in the nose of the fuselage, certain portions which are more subjected to impact of one kind, bird hits. There could be others, just the maintenance engineer dropping a tool. So there could be certain other regions also which are subject to it, but the fact that these happen on ground and therefore the inspection can also be performed, it's not on flight, so you do not have too much of an issue over there. Again, if you take the engine itself, you would see that within the engine there are certain requirements from the federal authorities, the certifying authorities. For example, in the very rare situation of a blade out, that means that one of the blades of the, let's say, the fan or let's say the compressor gets off from the hub, then the requirements are that for certification you actually have to test and show that blade will not come out of the engine containment. So you have what is known as containment structure which absorbs that energy of the impact, and does not let it come out, because once it comes out, it hits the wing or it hits the fuselage. It could be a much more disastrous consequence in terms of the fatality, in terms of the overall damage for the aircraft, etc. So depending on that particular material, so the kind of material that you might use for the containment structure would be materials like not carbon. You would instead use what is known as aramid fiber, which is commercially known as Kevlar. So Kevlar or aramid has very large ability to absorb the impact energy, because essentially it's a polymer. So not only your matrix is polymer, but the fiber is also polymer, very strong and stiff polymer, not as strong and stiff possibly as your glass and or carbon, but in terms of the ability to absorb the impact energy, it's much more. So in other words, it can deflect quite a bit, and that deflection can take some bit of the energy. In addition, it can undergo damage. Damage is allowed, but just that you don't want it to come out. So the blade goes and sticks into it, makes a hole into the containment structure. It can get stuck up there but doesn't come out. So the energy is absorbed not only in large deformations, but in the damage that the particular structural component or material undergoes. So both of these together make certain materials more suitable for the impact prone areas, but not all areas are so impact prone. So most of the areas as the primary structure that you're designing are the internal structures, let's say the spar within the wing, which takes a huge amount of the load. The stringers take very large axial loads. Then you have similarly the longerons, etc. here. So all of these are internal structures, internal reinforcements, rarely subjected to impact kind of a situation. So there composites can have huge advantages without having many of their so-called disadvantages.
Sir, but at this point of time, is there using the composite material, or they are?
Yes, these two, both these aircraft use almost 52% of their weight, structural weight, as the composites.
As
So
a load carrying member?
yes, primary load carrying members. Yes. So it's only a few portions of the primary load carrying member which are susceptible to impact, for example, which still use metals, but mostly it is the primary composite. But these are exceptions, and these have been around only for 15-20 years. But prior to that, what you're saying is absolutely true, that composites, even if they have been used, they have been mostly in secondary structures, which are where load carrying was not their primary function, or for example doors and things like that. Even today in a lot of these automobile applications also, you find a lot of composites being used, especially natural fiber composites, etc. Even by top companies, they use it only in the regions which are not primary structural load carrying members. So that's always there, but things have changed quite a bit in the last couple of decades, and you find much more extensive use. In fact, carbon composites have been used for since the 1960s in some very few aircraft applications. It's only large-scale application that I'm talking about, which has happened in the last couple of decades. Even in the 1930s, there was on an actual flying aircraft, there was a composite usage. So you can actually Google and see there are quite a few examples, but more of exceptions at that point of time. But now it's becoming almost a regularity, because you know the apart from the advantages, you know the disadvantages, you know ways of overcoming those disadvantages. For example, we talked about this. This is a huge disadvantage, that if I continue to use this and this, there's going to be galvanic corrosion. But instead, if I move to titanium, wherever aluminum was still being used, then of course I have to bear the higher cost, but nonetheless it can reduce its proneness to corrosion. So that's essentially what you're trying to do. So there's some way of ingenious way of counterbalancing these disadvantages is what you have to arrive at. Yeah. Okay, so that's as far as the dynamic loading is concerned. It's over a fairly wide range of frequencies. We discussed some of these, and I was talking about the flexural dynamic modes because of lift. the flexural mode because of drag, the torsion again because of the aerodynamic load distribution, and axial loads in the case of helicopter rotor blades. But these are not typically decoupled modes. These are all coupled modes with each other. So you would have the flexure and the torsion, for example, coupled with each other, and there could be fairly complicated couplings that you are having in those situations. So not only do you need to consider over a wide range of frequencies, but also in terms of the actual modes of deformation, they could be quite different. So the dynamic loading that you need to consider is very, very significant. But as I pointed out in the previous class, the advantage we have that is that all of these structures are such that either one dimension is very long or one dimension is very small, because of which the problem breaks up. It's not no longer from a spatial dimension point of view. You no longer have a 3D problem to solve. Your 3D problem breaks up into two parts, which is essentially your 2D plus 1D. So in the case of a plate or a shell, the plates or shells reference surface, you would have to do a 2D analysis, and the 1D analysis will be through the thickness. On the other hand, the ulta happens, the reverse happens in the case of your beam, where this becomes your cross section, the cross section of the beam, and this becomes the reference curve, or reference if it's a curved beam, or it's a reference line if it's a straight beam. So now out of these two, you would see that in terms of the dimensions that are involved, of course this is an area and this is length that we are comparing, but the area is made out of two components to it in the cross section. So the cross sectional dimensions, if you see, are very, very small compared to the reference curve dimensions. And similarly over here, you would see it's the other way around, that the reference surfaces dimensions, for example, the length and the width of this plate is very tabletop, is very large compared to the thickness that you have. So on the other hand, for the beam, the cross-sectional dimension, both the height as well as the width, is very small compared to the length of that beam that you have on the top over there. So this advantage means that there is a smaller quantity in both cases, and then there is a larger quantity in both cases. Okay, so there is your reference curve or the reference surface. Now the advantage of what we are going to do, the way we will progress, very similar to along similar lines to your textbook as well, is that this breakup we will do, and this breakup we will primarily be looking at the smaller dimensions where the dynamics doesn't play a huge role, even when you have all these coupled modes, and or you have the complication of, let's say, very low frequency, which is almost like statics, all the way to very high frequencies, which is your impact kind of a loading. In all of these, the dynamics affects only the larger dimension of the problem. Mathematically, it can be proven. It has been rigorously proven. It's beyond the scope of this course to detail that, but those of you who are interested, I can point out to references which you can look at in order to understand that. So when we are dealing with these two, which is the major portion of this course's syllabus as well as your textbook, you would see that we are actually dealing with statics. And you might wonder, in one of the beginning classes, we have already told the difference between aerospace structures and civilian structures. One of the main differences is in terms of dynamic loading. Still, why are we considering static problems? The reason is that these smaller dimensions continue to give very good results when you're doing with the, because of certain mathematical background to it, they continue to deal, you continue to deal with them using statics, you would still see that they are going to feed into this problem in terms of the properties. This is going to feed into this in terms of properties, but the actual analysis of this and this is going to be done in a dynamic sense. There you cannot avoid dynamics. And there, because of the complication of the overall geometry, if you're looking at a reference surface, which is, let's say, the mid skin reference, you have the outer portion of the skin, the inner portion of the skin, and then you have the mid thickness. You have the reference surface of the skin. You see how curved it is, and it's a doubly curved structure that you have, except in the inner portions where you could probably have curvature only in one direction, but in most parts you have a curvature in both directions. Fairly complicated, and there typically you will not be dealing with textbook like formula, or you will not be dealing with even things that you can do on a calculator, etc. You typically will be using computational codes, finite element analysis in particular, to be dealing with these two. But how good those finite element analysis results are will depend upon what this is going to feed in terms of information to this, what this is going to feed as information into this. That is very, very critical. If you do not do this part properly, then however good finite element code you might have, and however well you're knowledgeable about that code, and you're not doing garbage in, garbage out, you're taking care of the fact that you're putting the right kind of data, but because this part of the analysis has not been done properly, that is going to suffer. So that is a very, very critical part of what the structural engineer does in terms of the shaping of the cross-section shape for a beam, and in terms of the thickness, how it is distributed along the, let's say, the span of this wing. You may not have the same skin thickness as you go, even on the top surface, let us say, of the wing. You will not have the same thickness as you go from the root of the wing to the tip of the wing. It could change. Typically, it reduces in thickness. In other words, if you're making it out of a composite, you would typically have more number of layers to start with, and slowly you might drop a layer. So here it is 2 layers, and here it is 1 layer. Typically, it's in the order of 80, 100, few like that. But what I'm telling is, essentially, you have a ply drop. So once the ply drops, you have a thickness, and also it's not discrete. It is in some way the excess matrix is used so that it's kind of a smooth change in the thickness that is accomplished. But essentially what you're doing is the total number of layers are reducing, and you have a structure like that. Again, the geometry is quite complicated even in the plan form. If you look at how the taper is happening in the chord, and at the same time in terms of the sweep and other things, because the loading is going to be dictated by the direction of your velocity vector. So the velocity vector, whatever it is, you know, perpendicular to that is going to be your lift, and parallel to that is going to be your drag. So you have to, what the aerodynamicist or the flight mechanics people will calculate and give to you are these values. And now compared to the beam, it is at a different angle that it is coming because of the sweep. So you have to make an account for all of these things in terms of your original design of how you're going to put the fibers, and how many layers, and how they are going to be stacked up over each other. All of those decisions are going to be made based on that. So in, as I passingly mentioned in one of the earlier classes, one of the advantages of going for composites is also that you're going to have what is known as co-curing, or integral manufacturing of various parts. So if this aircraft, let's say, was being made much earlier, an earlier version of this entirely out of metals, you would have seen many more parts out of which the wing is constructed, and they are all joined to each other through rivets and countersunk bolts, the various other ways of joining. But today you have large, very large portions which are being baked in huge autoclaves, and if out of autoclave processes are also being used for some very large structures, where you are going to utilize very few fasteners. In other words, the total number of parts are going to come down once you are going to use composites, and that's a huge advantage, because many cases the joint becomes the weakest link in the overall chain that you have of the structure, and most failures typically originate at the joint. And if you have lesser number of joints, you would have a much there are, of course, there are issues in terms of how you assemble these very large parts, how you transport them, etc. there are many ways of doing it. For example, Airbus has a concept of the beluga that some of you might have seen, how they transport, because these are made nowadays not in a single factory, but factories across the world in many different countries, even continents, and then they're shipped and eventually have to be moved to an assembly structure where assembly plant where the overall structure is assembled. And but the number of assemblies are much lesser. Each component of that assembly becomes much larger, and but nonetheless you still have some joints still happening. They could be rivets. Many cases for composite to composite, it is adhesive joints which are taking over. But still, there are certain regions where the FAA doesn't certify the adhesive joint by itself. So you need to have a redundancy in terms of a riveted joint, at least because we are in a transition stage as far as this technology is concerned. But nonetheless, joining technologies become very, very critical in an aerospace industry. It has been much more critical in the past when we used only metals and smaller parts to join, but now it is reducing. But still, adhesive is a whole different ball game compared to rivets and bolted joints, which people have known, and a lot of empirical ways of handling that were already well established for a long period of time. But adhesives have been used more for typically domestic use and things like that, but not on large structures like these. That has been happening only in the last 2 decades or so. So there's a lot of uncertainty, and wherever there is an uncertainty, the certification agencies move very slowly, and that's why still joining technologies play a very critical role. And finally, the major difference between these two is in terms of the cost, how it dictates the overall performance. Economics always plays a role, but it plays relatively speaking, a lesser role in aerospace compared to in civil engineering structures, especially you weigh it in terms of what is the extra range that I can get, what is the extra speed that I can get, what is the extra payload that I can carry, because you're working in terms of the economics, not just the initial cost of the aircraft, but your running cost over its entire life cycle. And typically most aircrafts are used for 30 years or so over a large number of flights, and therefore it's not only in terms of the fuel burn, but also what kind of MRO operations it goes through, the maintenance, repair, and overhaul, what all kinds of things it has to go through. All of that becomes a huge cost. Even if you leave out the fuel cost, which is huge, MRO costs over an entire lifetime of an aircraft might turn out to be much more than your initial aircraft cost. So that's I mean, many of you who have two-wheelers or four-wheelers know, typically, especially higher end ones, if you give it for service, how much they charge. So typically it's not very different in terms of the business model as far as aircraft MROs are concerned as well. And at least in the case of two-wheelers and four-wheelers, you have many more service providers, and therefore there's a lot of competition between them, because of which the costs have come down quite a lot because of the volumes that you have. Whereas in the case of MRO for aircraft, there are very few providers across the world. There are very few countries which are capable of this, especially for larger aircraft, things like that. So you have to, it reminds me, when talking about the galvanic corrosion, there was a case where because of the usage of carbon and aluminum, there were a few holes which were observed in an aircraft, and because of which it could not be repaired in India. It's an aircraft which flew to India, but then the aircraft had to be flown out without passengers in order to get it repaired in the UK, because that particular kind of repair technology was available only there. So you see that the costs that are involved, not only in the actual performance of the MRO, but also because of the fact that these are available so far away, just taking the aircraft which needs an MRO to a different location, that itself can involve a huge cost as well. So all of this has to be accounted for, but at the end of the day, for a small increase in performance, we are able to say, okay, go ahead, because for example, the carbon fibers or titanium, so costs a bomb compared to your aluminum alloys or many of the conventional materials that you've been using for long. But the payoff is so large that the overall economics So in other words, you start seeing the bigger picture rather than focusing on something small. So what is an English proverb called penny wise, pound foolish? You're not doing that. So essentially, you're trying to see what is the bigger picture. If you're able to save money over a longer period of time in a much more scaled sense, you're willing to give that initial cost, a much larger initial cost. Most of these things are typically leased out or bought on loans, etc., by companies. For example, the Akasha airline that is there today, the amount of investment that it has got from Rakesh Jhunjhunwala, apart from Vinay Dubey, the owner, and CEO, is humongous. So people are willing to give that initial push when they see a vision that it can pay off in the eventually. Leave alone airlines like that. Even if you look at the Boeing 787, you see that the Dreamliner, the initial few aircraft that they sold, at least according to Boeing themselves, was under a huge loss. The per unit cost that they were having was the per unit sales cost was much lower than what they had spent on making it. But over time, it kind of pays off. And this is a model which is very commonly known as the printer model, because in printer technology also, you see the cartridges are much more expensive over a period of time. So many of these printer manufacturers like HP are willing to sell printers at a very low cost because they just want to get you. Once you have the printer, you need the cartridges over a period of time. And that's where the profit margins are much larger. So all of these the business model, the geopolitics, everything plays a role over here. And as engineers, we should, even if we don't know all the details of it, may not be possible also, but at least we should be aware of these things in the decision-making process. Yes, there is a lot of things that we make changes based on the engineering decisions, and that's what this course will be focusing on. But we should also be aware that this by itself doesn't make all the decisions. There are a few other outliers that we need to consider at times. So that's as far as that is concerned. Then probably we'll move to the next one. So the homework that we have. Yeah. So I don't want this to be looked at as a composites course. We have a separate analysis and design of composites course that in the department, AE224. I think it's offered this semester, next semester. So some of your specializing in structures can take that. There's also a non-linear mechanics of composite structures that I teach. So this is not kind of doing redundantly what they are doing. So those will be a little more advanced ways of looking at it. But at the same time, this is to give you an overall flavor for you, and most of it in a qualitative sense. And that's how this particular first assignment is also designed. So what I want you to do is that take up one of the helicopters being designed and produced by HAL, RWRDC, Hindustan Aeronautics Limited in Bangalore. Some of it is being done in Tumkur as well. So the LUH is the light utility helicopter. There's also another version of it called the light observation helicopter, or LOH. And then there is the light combat helicopter. The previous batch, one of the previous batches that we had, was working on the ALH, which is the Dhruv, and the LCA, which is the Tejas. So I've changed that assignment here, but in terms of the qualitative sense of what requirements we have, it's the same. So choose one helicopter, one of the aircraft. Oh, that's because I'm touching. Okay. Yeah, one of the aircraft which is made by NAL, National Aerospace Labs. HAL is also involved to some extent in that, but it's basically a baby of NAL. Also, Taneja Aerospace, a private aircraft company in the outskirts of Bangalore in Hosur, is involved with the production of those. Mahindra Aerospace also has some role to play in that. So these are all very exciting things that are happening. There's also the RT-70, a 70-seater regional transport aircraft that NAL has been working on for quite some time, and you could see news about that in the near future. But let's keep that aside. So one helicopter made by HAL, either of these two. One of the aircraft which is made by NAL. This is just a trainer, it's a two-seater. This is more like 19-seater. Of course, there can be various versions by modifying the interiors. So that is, and the reason why these have been chosen is that there's a huge usage of composites. So when we think of composites, we think of just, let's say, an American aircraft or a European aircraft. No, Indians have been doing quite some work in this particular area, and the Tejas as well as the Dhruv are examples of that for almost a couple of decades now, and there may be various others. Then also take up one of the launch vehicles of ISRO, the Polar Satellite or the Geostationary Satellite Launch Vehicle. One of the things I give this assignment as the first is one, of course, you get used to the terminology, the kind of references that you need to look at for various aerospace related problems, not only as part of your degree, but also eventually as part of your career. But even more importantly, I want you to collaborate amongst yourself, because there are quite a few from armed forces, there are a few from the DRDO, from ISRO, etc. And there's some dual use technologies that are involved in terms of these rocket motor casings, etc. So people will be aware of these things. Of course, don't use any of your confidential data. Those of you from ISRO, Armed Forces and or DRDO, obviously you will not use it, but don't be pressurized to use or share any of that data. We are only looking at what is available in the open literature, and there's quite a bit that is available in the open literature. So take one of the helicopters, one of the aircraft, one of the launch vehicles, and what I want you to do is that I want you to see, like in these examples that are shown over here, which parts of the structural parts of the aircraft are using which type of materials, and not just stick to composites, but the other materials also, be it aluminum alloys, titanium alloys, steel in some locations. As we discussed earlier, for example, many landing gear components are made out of steel. But what is most important for me in terms of the response from you is this last part, why. Because other things are all information that you seek from different sources. I want you to give the proper references as well. And don't email that, submit it through the Microsoft Teams that you are all a part of. And if you have any issues, you can contact through that email, and Rajesh will be able to give you certain leads on how to handle any issues that you might face. But I want you to primarily focus on this. But if you want to focus on this, first of all, you should have enough information. Otherwise, what are you going to be talking about reasons for? So you collect all that information. It's okay if you get together and do it, not an issue, but essentially I want everybody's contribution to be kind of visible. There should not be any dead baggage. I'm part of this team, but the others are doing the work. I'm just hanging on. So I want to ensure that everybody is contributing in some sense. That should be visible in your submission, because your submissions will be individual. And you can also mention when you're giving references of which websites you're taking from, which books you're taking from. For example, one of the good sources is Jane's All the World's Aircraft. Many of you might be familiar with that. I think our library subscribes to that. So it's an encyclopedia for all the aircraft that have been made right from the beginning up to the latest. And whatever information is available, typically they try to source it from various, both the OEMs as well as various other sources, and they try to put it up there. So that is one source. And of course, the internet, YouTube, many different sources are possible. But give the right reference for all of them and explain why. So to give you a very simple example, I think we already talked about some of these things. For example, you were asking whether primary structures are being made. So these are the two aircraft of which I was showing you the models. This is the Boeing 787 and the Airbus A350. And both of these, you can see that huge percentage of the primary structures are being made using composites, carbon fiber epoxy composite in particular. But you would see that still a lot of these leading edges and certain areas which are prone to impact, for example. So it was kind of a giveaway when I said that, because that is the reason why it is used. But you can probably look at other reasons for it, as well as try to go a little dig a little deeper into it. And are there some examples where composites are being used in the lead? For example, here also you see the nose also is subjected to impact, so you would not use the carbon fiber. You would typically use a metal for that. So again, these are passenger aircraft, which we were seeing earlier, but whether it's a fighter aircraft, either abroad or in India, or a helicopter, you would see that it's all very similar to that. Sometime any of you can come to my office, I'll show you for the advanced light helicopter the tail rotor, which is made out of a combination of carbon epoxy and glass epoxy. And you would see that the reason why one is used in certain regions and the other is used in some other regions would be quite evident once you see that. And it's very easy to distinguish them even visually, because the carbon fibers are darker in color compared to the glass fibers. So you would see a distinct color difference when both are used in a hybrid kind of a composite. So are there any doubts in this? This is kind of self-explanatory assignment. You would see many such examples in the literature in terms of these kinds of cutouts. These kind of cutouts really help you to see in terms of the spars, the stringers, etc., what is typically utilized. And there are certain things, of course, for fighter aircraft, etc. The things are kept confidential for the interior details, etc. But nonetheless, whatever information that you can lay your hands on and the reasoning based on that. And though the aircraft that I'm talking about are all Indian aircraft, for the reasoning, some of the information that you have, a large amount of information on these two aircraft will help you, because in a qualitative sense it is the same. If particular location they are using a metal over a composite, what is that particular reason, and which particular metal, and why that choice of metal. So the reasoning might be somewhat similar in the case of these aircraft as well. You might not find exact same thing mentioned for this aircraft, but the qualitative arguments might be similar. So I think with that we'll probably end today's class. If you have any questions, I'll have. However, how do you prefer? PDF? Yeah, you can make it as a PPT, and you can save it as a PDF and send it. But a document or PPT, but submit it the final version as a PDF. 1 week. For all assignments, as I mentioned in an earlier class, it will be 1 week. So today's assignment, today being Friday, it will be next Friday. Yeah. Okay, thank you. Yeah.
What is the kind of difference and purpose of carbon laminate and carbon sandwich?
Okay. So carbon laminate is typically when you are using a carbon fiber in an epoxy and many layers of that. It's just essentially a carbon laminate. But once you have a bending problem, this is not a typical case, but suppose this was a small aircraft. In a small aircraft, you're not using, let's say, spars and or stringers. You just want the skin itself to be able to handle the bending. Now the wing is going to bend because of the lift, right? Now bending, as you know, will require a large EI, that is the bending moment of inertia. Apart from the choice of material E, I should be large. Now you don't, the thickness of the wing is not decided by you as a structural engineer. The aerodynamicist has already decided it. So how do you go about doing that? If you make it whole solid, it's going to weigh a lot. So weight penalty will make you not go for that. So what people do is go for a sandwich. Very similar to the sandwich that we eat. We have two breads, loaves, and in between you have some material there, right? So same way, sandwich constructions have very stiff and or strong outer layers, what we call as face sheets or face plates, which could be made out of similarly like carbon laminates. But in between you have a softer, lighter material that could be a foam, that could be a honeycomb kind of a construction, whatever that is, but essentially it is so light because you know that there the bending stress is not much. The tension and compression that are going to come are in the outer layers, which is taken by the carbon laminates that you have, what is shown in blue over there. But as far as what is shown in the light blue is concerned, you have that also, but in between you have the softer material which will take the transverse shear loads. So for example, this bending is not coming because of a pure bending moment that you are applying. It's because of a distributed lift which is causing not only bending but is also going to cause transverse shear in this direction. The drag is going to cause transverse shear in this direction. Now that can be taken by these soft materials. Even though they are soft materials, they may not be good in tension, they may not be good in compression, but they are very good in shear. So they will take the transverse shear, and you know that for a typical rectangular cross section, the transverse shear is distributed parabolically. In other words, the outermost are not going to take much transverse shear. They are going to take only the tension and compression coming because of bending. The inner one is what is going to take the transverse shear. And so there you choose the right material. So this in a sense is explaining exactly the kind of reasoning that I'm looking at for overall components. I'm talking of components like let's say a rudder, what is used, why, for rest of the vertical tail, what is used and why. That's what but here I'm trying to explain it from an even more lower point of view in terms of the structural build-up. That this is the kind of arguments that I'm looking forward to. Yeah. All right, thank you.